Bismillahirrahmanirrahim. This is lecture number 12, the continuation of chapter 6 from the book. So in the last lecture, what we studied actually, it was about the single wavelength. So here in this lecture, I will try to explain briefly a single frequency operation. If you remember the previous two lectures, that is 10 and 11, probably you can understand easily here. क्या होता क्या है कि ये आपको याद होगा, ये शो किया था मैंने लास्ट लेक्चर में या उससे पहले, कि अगर आप ड्रॉ करें फ्रीक्वेंसी और आउटपुट पावर तो you can see these spikes which is under the gain curve. Okay, so इसके अगर हम एक small portion को magnify करें, if we magnify here, then you can see it's like this. So what is this? Actually small section of output. So what it shows, individual modes in the gain curve. Individual modes in the gain curve. Now, if you see here, what is written here, okay, an organ laser, this is, we are taking as an example. Okay, organ laser को हम यहाँ पे as an example ले रहे हैं. Has a relatively large bandwidth. Okay, so क्योंकि आर्गन आयन लेजर जो है उसकी बैंडविड्थ है वो relatively large है as compared to the many other lasers. तो allowing a large number of longitudinal modes with slightly different frequencies to oscillate simultaneously. क्योंकि इसकी बैंडविड्थ बहुत जो है वो लार्ज है, ठीक है, इसमें नंबर ऑफ लॉन्गिट्यूडनल जो मोड्स है ना वो इसकी गेन कर्व में होते हैं, ठीक है, with slightly different frequencies. Okay, और ये simultaneously जो है ना वो oscillate करते हैं, like this you can see here. Now in this slide, this is the same figure which you have seen the last slide. और इस portion को अगर हम magnify करें, let's suppose if we take this portion, तो before to go to this graph, we have to know how to choose a single frequency. उसके लिए जो हम यूज करते हैं, जैसे कि वेवलेंथ चूज करने के लिए हम प्रिज्म यूज करेंगे या ग्रेटिंग यूज करेंगे कैविटी के अंदर. बट हियर इफ वी वांट टू चूज फ्रीक्वेंसी और सर्टेन लॉन्गिट्यूडनल मोड्स, तो उसके लिए हम एटलॉन यूज करते हैं, ठीक है, इट्स काइंड ऑफ कम्पैक्ट इंटरफेरोमीटर, ठीक है. या तो दो glass, like if this one and the waves will be oscillating here like this, the etalon. Okay, so we use a piece of glass inside the cavity, you will see in the next slide. So that will help us to choose a frequency, okay, to decide longitudinal modes. Now what is written here, if an etalon like a compact interferometer, okay, इसकी जो width है that will decide. Okay, That is why it's called the compact interferometer. Okay. So if we design in a way that it resonates only at a wavelength spaced further apart than the 5 gigahertz, okay, how we find a wavelength? We can find out wavelength from the frequency, and we can find out the frequency for the wavelength. Okay. तो यहाँ पे ये क्या कह रहा है कि if etalon it's like a compact interferometer, तो उसको अगर हम डिजाइन करते हैं कोई certain wavelength, ठीक है, but specifically here it's mentioned 5 gigahertz because we are taking as an example this 5 gigahertz is for the organ laser. Okay. So in this case it resonates only at a wavelength space further apart than 5 gigahertz. 5 gigahertz को आप wavelength में convert कर लें. So जो उसकी wavelength इसमें convert करके ना 5 gigahertz को, अगर तो ये resonate करे further apart more than 5 gigahertz bandwidth laser, तो उस सूरत में हम सिंगल मोड जो है वो अचीव कर सकते हैं. और if we can have a single mode, that means a single frequency, that is the longitudinal modes. Okay. So excuse me, the spacing of the resonant peak of an attolan, उसकी जो spacing है उसको हम FSR, if you remember in the beginning of this chapter we have discussed FSR, free spectral range of an attolan कहते हैं. जो peak की spacing है, जो longitudinal modes हैं आपके, उसकी peak की जो spacing है उसको FSR, free spectral range कहते हैं. ठीक है. और that's happening with atolon as well, कि हम वही चूज करते हैं स्पेसिंग को यूटिलाइज करते हुए. ठीक है. Like the spacing of the resonant peaks of an attolan, spacing of a resonant peaks, जो उसके दरमियान वेव जो रेजोनेट करेगी, ठीक है, उनके से हम डिजाइन करेंगे. उसके दरमियान जो गैप आएगा वेव का वो फ्री स्पेक्ट्रल रेंज उसको कहते हैं. पीक्स आएंगी लाइक दिस, लाइक दिस, लाइक दिस. ओके. So that is FSR. ठीक होगी बात, like this here. So only when a resonant peak of the attolan and a longitudinal mode of the laser have the same frequency, resonant peak of attolan, okay, like this, and longitudinal mode of a laser, like here, have the same frequency. So same frequency will have the laser have enough gain to oscillate. So what I said here कि उसकी जो रेजोनेट पीक है जो एटालॉन की और जो लेज़र की जो लॉन्गिट्यूडनल मोड है उसकी फ्रीक्वेंसी अगर मैच कर जाए, ठीक है, तो देन वी कैन गेट एट द आउटपुट फ्रीक्वेंसी व्हाट वी वांट. सो हियर ये एटालॉन की रिस्पॉन्स है, ओके, और यहाँ पे आपकी ये आउटपुट आ गई। ओके, सो दिस इज एक रिस्पॉन्स, फिर उसके बाद दूसरी रिस्पॉन्स, दिस इज कॉल्ड FSR, और ये फ्रीक्वेंसी, ठीक है, ये जो है ये इसके साथ अगर मैच कर जाए तो वी गेट एट आउटपुट द फ्रीक्वेंसी व्हाट वी वांट एंड सिंगल मोड, सिंगल longitudinal mode. Now this is the experimental arrangement how you can get single frequency. This is etalon, this is a wavelength selector, okay, ये आपकी कैविटी है, ठीक है। तो दिस इज कॉल्ड इंट्रा कैविटी एटालॉन। इंट्रा कैविटी में कैविटी के अंदर है, कैविटी के बाहर नहीं है, ओके, इट्स नॉट आउटसाइड ऑफ द कैविटी, इट्स इनसाइड द कैविटी। और वेवलेंथ सेलेक्टर दैट वी हैव स्टडीड ऑलरेडी, और उसके साथ अगर हम एटालॉन यूज कर लें, इफ वी गोना यूज एटालॉन हियर, तो वो क्या होता है, देन वी कैन हैव a single frequency, choose a wavelength, and you have optimized laser. Now go through the points here what is mentioned. A practical etalon consists of a glass slide, as I mentioned, can be quartz to reduce the absorption. Coated on either side with a slightly reflective thin film coating. Both the sides of this quartz glass, like here, it's coated. Okay. First thing, it's supposed to be coated that the wavelength what we want, okay, और ये slightly reflecting coating, इसे thin film coating कहते हैं। मटेरियल साइंस के जो हैं वो they can understand, वहाँ पे ये काफ़ी thin film coating जो है ना यूज़ करते हैं। In the second point here, the etalon acts as an interferometer, which is resonant only at certain wavelengths. The etalon acts as an interferometer, as I explained before, which is resonant only at a certain wavelength. ये उसकी thickness पे depend करेगा, उसकी coating पे depend करेगा। It is inserted inside the cavity of laser, which has a wavelength selector, as you can see, so that only a single line oscillate. Wavelength भी select हो गई, longitudinal mode भी select हो गया, that will help you to have a single frequency, and then all these things are happening, so this thing will oscillate in the cavity. A wavelength selector is required for a multi-line laser, ठीक है, जैसे argonine laser that we have already studied. लेकिन but if we have the helium neon laser, which is already optimized for the red wavelength, in this case we don't need this arrangement, okay. So it depends what kind of laser. This is specifically is actually this example in general is given, and an argon ion laser is mentioned again and again here. The reason is that this laser is used as an example, and it has a broad bandwidth. तो इसमें हमें wavelength select करनी पड़ती है. But if we use the helium neon laser, is already optimized for the red wavelength, then we don't need it. Only eta alone will be enough for the longitudinal modes and a single frequency. Here, this is something we try to explain about the eta alone. Eta alone is what? It's a glass slide. Okay. और इसकी जो thickness है वो depend करेगी what wavelength you are gonna have, और उस SPM frequency you can calculate. What is happening here? Two possibilities. You can also use two glasses. Okay, with a very, very small distance apart. Or you can use a hollow kind of slide here. What is mentioned here? Okay, this is input beam here. It goes inside. Okay. Some part is passed through, some part is reflected inside. Some part is refracted, some part is reflected. Okay, and then it goes out in the form of beam 3. So beam 1, beam 2, beam 3. It depends on the angle. It depends on the angle, what is the angle of this eta alone. Okay, this is a theta. Okay, and this is phi inside. And this one has to be like a 90 degrees here. Now let's go through this one. The points are mentioned here. One thing, the eta alone is always tilted with respect to optical axis. Okay, it has certain angle. Axis of the laser. Otherwise, it would act as a simple mirror. We have to make a certain angle here. Okay, it would have a simple mirror. So अगर हम इसको बिल्कुल सीधा यूज करेंगे तो वो सिंपल मिरर के तौर पे इसमें से पास कर जाएगी लेजर. ओके, सो वी हैव टू हैव सर्टेन एंगल, सो which would not select wavelength. ठीक है. What is mentioned here? कि eta alone is supposed to be tilted with respect to the optical axis at a certain angle. Otherwise, it would act as a simple mirror. ठीक है. और अगर सिंपल मिरर के तौर पे तो इट्स यूजलेस. ठीक है. सेकंड पॉइंट, an incoming beam, which is beam 1, as I mentioned, they enter the eta alone and is refracted. Okay, refracted. Beam 2, it refracts again upon exit and leaves the eta alone as beam 2. Okay, refracted from here, refracted from here. So it's refracted from here, refracted from here, and you get beam 2. Along with this one, a portion of this wave which is refracted from here is also reflected. Okay, as mentioned, but a portion of the beam, 20% here, I mean, typically is not 100% definitely, and not 50%. It depends on the coating. Okay, so for a typical eta alone with a low gain, it's saying about the gas lasers. Okay, it depends on the laser to laser. So is reflected from the coating on the side of the eta alone. From here is reflected, and from here is refracted, and reflected back into the eta alone along path AB. A and B, reflected, reflected. So beam is reflected again So the beam is reflected again, becoming B and C. B, C here. And is refracted, okay, from here again. And it forms a beam 3. Okay. Beam 1 enters, refracted here, beam 2, and the part of this one is reflected from here and reflected from here, and from here is reflected, and it becomes a beam 3. Okay. So important thing here, if the difference in the path length between the beam 2 and 3, this beam 2 and 3, is an integral number of wavelength for a constructive interference. Constructive interference occurs and the transmission of the etalon is seen 100%. Okay, not less, sorry, it's 100%. So what are the important points here? कि ये जो beam 2 और beam 3 here, they interfere. Okay. The path length between the beam 2 and beam 3 is the integral number of wavelengths. Integral number of wavelengths for the constructive interference. Okay. So we design in this way the spacing that you have a constructive interference. Okay. And in this way, the transmission of this etalon is 100%. Okay. So whatever the constructive interference, okay. So we get that जिस wavelength पे constructive होता है वो हम we can get the output. Point number 6 here, when the paths are not separated by an exact number of wavelength. Beam 3 exit the etalon with a phase difference from that of beam 2. In दोनों के दरमियान we have phase difference, beam 2 and beam 3. Okay. So the paths are not separated by an exact number of wavelength. What we know from the previous point, the integral number of wavelengths. Okay. But here, what it's saying, when the paths are not separated by an exact number of wavelength, then destructive interference होगा. Okay. And the transmission is low for this kind of destructive. So destructive interference जो होगा, that will not pass through all. It's very low. Okay, transmission is very low. So the transmission is 100% only for the constructive interference. This is how this etalon it works, and we get output beside the longitudinal modes and the frequency. Okay. So this is lecture number, I think, probably 12. I don't know. I don't remember now. Anyway, we'll continue the next lecture.